Okay, if things are going well, you should see a sheet that's entitled Acidity of Salts. Now, that's kind of a weird topic in a way because you might recall earlier I taught you that salts were neutral, except I had a disclaimer. I said most salts are neutral. It turns out some salts can be acidic or basic. Now, you'll notice I wrote the positive ion in red for A for acid. A positive ion can be an acid or neutral, never a base. The negative ion could be a base or neutral, never an acid. Now, I thought it was always kind of easy to understand how the negative ion could act as a base. If we're talking about putting this negative ion into water, it's possible that it may pull a hydrogen off of the water to form Hb, and what's going to be left of the water? Hydroxide. Okay, so that's always a possibility you want to consider, is a negative ion could undergo a basic reaction with water. What's a little bit harder to explain is how the positive ion could be an acid. It's possible the positive ion could give off a hydrogen to water and make hydronium ions, which is the active ingredient of an acid. Let me show you two examples of how this can happen. Okay, example number one, there are these things called ammonium salts where you have an NH3 to make hydronium ions, and we'll see some examples of that later. The second example is a little bit harder to understand. Here's a case where you have a zinc ion that's hydrated. It's surrounded by 6 water molecules. You put this into water, and what happens is zinc ion pulls so harder on the water molecules that one of the hydrogen ions pops off and forming the hydronium ion. Now notice what's left of the zinc, okay? The zinc is still surrounded by 5 water molecules, and the one that lost the hydrogen is now an OH on the zinc. Now, copy down example number 2 because you're going to need it to complete experiment number 9. In experiment number 9, there's going to be a question where they ask you, how can the zinc make the water acidic? And you're going to copy down this reaction. No need to memorize it, but we're going to find out how good your notes are if you complete experiment number 9. By the way, experiment number 9 is going to be next week. And so if you have Monday lab, it'll be during Monday time. Wednesday lab will be Wednesday time. And obviously you can't do the experiment. So what I'm going to do is I'm going to give you some raw data. I'll explain how to do the calculations. You do the calculation part of the experiment, and then you'll send me a copy of your result. Okay, let's see some example chloride. Now, what you always want to do is you want to break up the positive and negative ion and put them into water and show the 2 possible reactions. Now, there's a wonderful, wonderful shortcut. And if you recall from the last lecture, some ions are spectator ions. That means they do not react with water. So on example, show me both reactions, and the one with water, just cross it out. So notice where I put this double green here. Yeah, so chloride should be on your list of spectator ions. It does not react with water. That saves you a lot of time. Just to refresh your memory, what the spectator ions are would be members of family 1A, positive ions, family 2A, the positive 2 ions, family 7A, the negative 1 ions except for fluoride, and also nitrate. Okay, so we can forget about the chloride reaction. Let's look at ammonium. Okay, now the possibility is ammonium could give a hydrogen up to water, form the hydronium ion, and the ammonium becomes ammonia. Now, here's the deal. On exam, I'm going to say prove whether a salt is acidic or basic. The proof is, if you think the reaction takes place, you've got to come up with the equilibrium constant for that reaction. In this case, you've got to come up with the equilibrium constant for the ammonium ion. Now, the question mark is, can you find it? Now, on the exam, it's going to be an open book exam, so you can look around for tables. You may be lucky. You may find a table that shows the case of A for ammonium. If you don't, you have to give it one more chance. Now, what do I mean by that? Remember last time we learned that case of A times case of B equals case of W? So therefore, you could solve for case of A by algebraically rearranging this. It's equal to case of W divided by case of B. What B? The base of ammonium, which is ammonia. So go back and look at the reaction. So ammonium acid's conjugate base, ammonia. So therefore, you could indirectly calculate the K sub A of ammonium by dividing the K sub W by the K sub B of ammonia. And I guarantee you will find the K sub B of ammonia on a table that will be there. So mathematically, K sub W is 10 to the minus 14th. You'll find K sub B for ammonia to be 10 to the minus 5. Do the math. The answer 10 to the minus 9 means yes, the K exists for this reaction, and therefore it would be acidic. Okay, example number 2. Let's look at the salt potassium chloride.
Yes.
So again, you want to divide this into 2 reactions. Put potassium into the water, put chloride into water. The potassium is a potential acid, the chloride is a potential base. But this is where your memory kicks in, and they are on your spectator list, so they do not react with water. So on exam, just show the reactions, put slashes for the spectator reactions. Your conclusion is this must be a neutral salt. Okay, let me give you a moment to try number 3 on your own. So the salt is sodium acetate. Now we do an awful lot with acetate, and its formula is C2H3O2. A lot of times we abbreviate in chemistry as just AC. So we'll give you a moment to see if you can take this. So what you should do is write the 2 possible reactions. If there's any spectators, that'll give it a shortcut, and then prove whether the reaction is positive or negative by figuring out if it has a K sub A or a K sub B. Okay, the answer. Okay, so I've written the 2 reactions for sodium into water and acetate into water. Okay, so your memory kicks in. Sodium is a spectator, so no reaction there. That's good. Okay, acetate is not on your memory list. Okay, the fact that it's a negative ion makes it a potential base. So notice I've started the Bronsted reaction. It pulls a hydrogen off of water to form molecules of HAC, and the water now becomes hydroxide. Now, just because you write something on paper doesn't prove a darn thing. You have to be able to calculate the K for the reaction, and it helps if you know what kind to name that K. So the acetate is acting as a base, so you need the K sub B of acetate. I've never seen the K sub B of acetate on a table, so you got to give it one more chance. What's the one more chance? Use K sub A times K sub B equals K sub W. So rearranging that, K sub B would be K sub W divided by K sub A. And what's the acid? Acetic acid. So K sub W, notice, is 10 to the minus 14th. And you can look up the K sub A of acetic acid. It's 1.8 10 to the 5. You do the math. The fact you get an answer of 5.6 10 to the minus 10 means this reaction does take place. So this would be a basic salt. Okay, let's actually do a mathematical problem now with this idea. So the problem goes like this. Calculate the pH of a 0.080 molar sodium carbonate solution. Just as before, you want to look at the positive ion, which is sodium, and the negative ion, which is carbonate. Okay, the shortcut is sodium's on your spectator list, so great, we can forget about that. Now, carbonate's not on your spectator list, so treat it as a Bronsted base. It pulls a hydrogen off of water, forms HCO3, and hydroxide. Okay, so it looks like you're going to have a basic solution. Now, you need the K for that reaction, and what's its name? It would be the K sub B for carbonate. Now, I've never seen the K sub B of carbonate on a table. So we're going to use the good old trick that K sub B equals K sub W divided by K sub A of its conjugate acid. Now, here's a problem. Where are you going to find the K sub A for hydrogen carbonate? Okay. You're going to find it on a table for carbonic acid. Remember, carbonic acid is a diprotic acid. It goes under 2 steps. Step number 1, it gives off the first acid hydrogen. And then step number 2, hydrogen carbonate gives off the second acid hydrogen. So the tricky thing is the K we need for this reaction is the K sub A2 for carbonic acid. Let me state that again. You won't find the K sub A for carbonate, or you won't find the K sub A for hydrogen carbonate. It'll be the K sub A2 for carbonic acid. So you have to be aware of the 2 reactions carbonic acid went through. So now here's the mathematics. So K sub W is 10 to the minus 14th. Okay, the K sub A for hydrogen carbonate is 1.6 to 10 to the minus 11, giving us a K of 1.8 times 10 to the minus 4. Now we're not done with the problem, but at least we have the K for the reaction. So if this makes sense, let me go on to the next sheet. So the starting concentration is given as 0.08 molar. You can assume plenty of water. No mention of these guys yet. Okay. Now, because of the small size of the K, you're also looking at the completion step. It favors to the left. Okay, you can't have zeros, so here comes the change step. So now we get some action. Minus x, these two react to give you positive x, positive x. Okay, sum everything, and you get 0.08 minus x for the concentration of carbonate. Notice I don't bother writing water. Remember, water is a solvent. It's present, but it isn't involved in the mathematics. And you got x for hydrogen carbonate, x for hydroxide. So here's our goal. If we can solve for the equilibrium hydroxide ion concentration, this x right here, we can get the POH in there for pH. Okay, so plugging into the mass action expression. So the constant is equal to products, which are x and x, divided by the reaction carbonate, 0.08 minus x. Okay, you can ignore this x right here. Okay, I already stepped ahead a little bit, so I figured out x squared, took the square root, I got 3.78 times 10 minus 3. That's the hydroxide ion concentration. Okay, take minus the log of that, you get the POH, you get 2.42. Subtract your 14, you get 11.58. As a double check, okay, think of a pH meter or pH scale. Okay, if you get a pH higher than 7, it should be a basic pH, and sure enough, this will be a base. So I hope you follow the mathematics on that. Okay, okay, you're now ready for super killer. So superkiller goes like this, okay? The salt is ammonium cyanide. Now, what makes this a little bit hard is neither of these are on your spectator list. So they're both potential reactions. So let's look at the potential acid reaction, the potential base reaction. So the ammonium could act as a Bronsted acid, give a hydrogen to water to make hydronium, and here's its conjugate base. But cyanide is not on our spectator list, so it's a potential base. It could pull a hydrogen off of water, make HCN and hydroxide. So now we have a problem. We have a potential acid and a potential base. Who's going to win out? Well, the answer is we have to figure out the K for both of these. We need the K sub A for ammonium and the K sub B for cyanide. You probably will not find these on a table. So you have to get one more chance. What's that one more chance? K sub B times K sub B, K sub A times K sub B gives you K sub W. So therefore K sub A would be K sub W divided by K sub B, and the base of ammonium is ammonia. You'll definitely find the K sub B of ammonia on a table. So mathematically, it's 10 to the minus 14th divided by the K sub B of ammonia is 10 to the minus 5, we can answer 10 to the minus 9. So the reaction does exist. It does definitely produce some acid. Now let's look at the cyanide reaction. So the K sub B of cyanide, you will not find that on a table. I've never seen it. You have to give it a second chance, which is K sub B is K sub W divided by K sub A of its conjugate acid, which is HCN. Okay. So mathematically, K sub W is 10 to the minus 14th. The K sub A for HCN is about 10 to the minus 10, and we do get an answer 10 to the minus 4. Now, why did Berg put a red box around this one? Because of the two Ks, this one is 10 to the 5th larger. That's 100,000 times larger. Okay, so they both take place, but the one that dominates is going to determine if it's going to be an acid or basic salt. Since the K sub B is larger than the K sub A, that means this salt would be a basic salt. Pretty good problem, don't you think, where both of them take place, and you have to figure out which one is going to be the dominant one.